Welcome back to another explainer. Today, we are unlocking one of the absolute fundamental secrets of structural engineering. We're going to completely demystify flexural stress in massive beams. Basically, we're breaking down the exact mathematical logic that keeps the buildings we live in and the bridges we drive across standing tall. Okay, let's dive into this.
So, it's a pretty high stakes question, isn't it? When you look at a massive, solid steel beam supporting literal tons of weight, it seems incredibly complex to predict its exact breaking point. It kind of looks like an unpredictable, chaotic problem. But as we know, engineers don't guess. They actually have a framework, a sort of structural cheat code, if you will, that shifts this wildly complex physical reality into a neat, predictable mathematical model. And here is our roadmap for how they do it. First up, the bending beam problem. Then we'll go through our three core kinematic assumptions: staying plane, the neutral surface, and linear strain. And finally, we'll use all of that to unlock the calculation for bending stress.
Now, to understand just how foundational these rules are, take a look at this actual university engineering exam for the mechanics of solids. Right there in question 1, part B, worth 3 marks, it asks to describe the basic kinematic assumptions of beam. This isn't just some abstract theory. This is a constant, highly tested requirement. Every single civil and mechanical engineer absolutely must master this before they ever design a real-world structure. So yeah, these are the stakes.
All right, section 1, the bending beam problem. Before we can even touch the mathematical assumptions, we really need to establish what physically and geometrically happens to a prismatic member, a beam with a uniform cross-section, when it gets bent. If you look at the grid lines on this beam undergoing pure bending, something really cool happens. When the beam is subjected to equal and opposite bending couples, it bends uniformly to form a perfect circular arc. Notice what happens to those perfectly square grid boxes. The beam naturally compresses at the top, meaning the squares squish together and decrease in length. Meanwhile, down at the bottom, the material naturally stretches out. It's just a beautiful geometrical transformation.
So to actually calculate the stresses inside this curving geometry, we rely on 3 key assumptions. 1. Sections remain plane. 2. A neutral surface exists. And 3. Strains vary linearly. This rule of 3 is really the core of our explainer today. Let's go ahead and break each one down individually.
Section 2, Assumption 1, staying plane.
This first building block sounds super simple, but it's literally the cornerstone of everything that follows. Now, what's really interesting about this slide is the behavior of those vertical lines cutting through the beam. Before the bending happens, they're perfectly straight up and down. But after bending, even though the whole beam is curved into an arc, those cross-sectional planes pass right through the arc's center, perfectly straight. Sure, they rotate, but they do not warp, they don't bulge, and they don't distort.
To really grasp what sections remain plane actually means in the real world, just imagine a really thick paperback book. If you bend the book, the pages fan out to accommodate the curve, right? They rotate relative to one another. But if you take any single individual page out, its surface is still completely, perfectly flat. Well, in our beam, the cut faces stay perfectly flat even as the entire object curves under massive loads.
Okay, moving to section 3, assumption 2, the neutral surface. Right, so now that we know our cross-sections stay perfectly flat, we need to find our physical anchor point inside the bending material. Remember how we said the top of the beam compressed and the bottom stretched? Well, logic tells us that if you go from negative compression all the way to positive tension, somewhere right in the middle, you absolutely have to cross 0. That is the neutral surface. And when you look at it straight on from a cross-section, we call it the neutral axis. It's basically the single layer of fibers inside the beam that neither squishes nor stretches. It is the ultimate safe zone. As you can see on the cross-section of this beam, that red line labeled neutral axis passes right through the centroid, which is marked O. Above this neutral plane, the material's fibers are negative compressive stress. Below it, they're in positive tension. It's actually a lot like bending a really thick stack of rubber bands. The ones on top bunch up, the ones on the bottom stretch out to their absolute limits, but the rubber band right in the dead center, it barely feels a thing.
Section 4, Assumption 3, linear strain.
All right, now for the final piece of the puzzle. We've got our flat planes, and we've established our 0-point anchor. Now we introduce the mathematically critical assumption that connects our visual geometry to the actual structural forces. So the crucial point is this quote, straight from the engineering principles. Strains in its fibers vary linearly or directly as their respective distance from the neutral surface.
Let me tell you, this right here is the absolute holy grail for calculating flexural stress. It means the deformation isn't just some random occurrence. It's a strict, proportional, mathematical relationship based exactly on how far away you are from that safe zone we just defined. And this brilliantly illustrates exactly what that linear variation looks like. Check out the red arrows representing the strain. At that dashed neutral surface in the middle, the arrow is basically non-existent, zero strain. But as you move upwards by a distance of y, the arrows get predictably longer, forming this perfect triangle until they hit the maximum distance, labeled C. The strain triangles get dramatically wider the further you move away from that neutral axis. To put it as simply as possible, when your distance from the neutral surface is zero, your strain is zero. When your distance is maxed out, way out at the very outer edge labeled C, your strain is at its absolute maximum. When you contrast that perfectly still, zero-stress neutral center with those highly stressed outer edges, intuitively, you can see exactly where a beam is going to snap first. It's going to happen right at those extreme top or bottom edges where the strain is maxed out.
Finally, Section 5, Unlocking Bending Stress.
So let's stack all of this together and see what we've built. We have our 3 kinematic assumptions, and they combine to unlock the ultimate goal of this explainer, finding the actual bending stress. By layering these rules, engineers pull off something pretty incredible. First, the flat planes simplify the messy 3D deformation into manageable geometry. Second, the neutral axis gives them a definitive, rock-solid 0 point to measure from. And third, the linear variation gives them the exact mathematical formula to calculate stress at any given point. This perfect stack of assumptions is exactly what allows engineers to treat highly complex, real-world materials, like massive steel I-beams or solid concrete, as predictable, fully elastic models. But I do want to leave you with a bit of a curveball. Everything we've covered today relies on the material staying perfectly elastic, meaning it snaps right back to its original shape the moment the load is removed. But what happens when the load is just so extreme that it pushes the beam way past its proportional limit? What actually happens when plastic zones develop and those residual stresses get permanently locked inside the metal? Well, that takes us beyond the elastic limit and definitely into our next explainer. Keep learning, stay focused, and I'll see you next time.